Welcome back to another session. Please, do you have any questions for me before we start today's session? Okay, now I have an announcement to make. So I think you may have received an email regarding like course evaluations. So the plan is to motivate you guys to do it, right? I am thinking of awarding some points, right, towards the final, if you do the evaluation and then send me evidence that you've done it. I don't need anything on it. Just send me, when you submit it, it will say submitted. So just send me a photo of that, right? So send me a picture of the submission, the proof that you submitted. So I'll see if I can award some points on the final, right? So please do that. So do your course evaluations. You can get access to that here. What do you call it? www.unr.edu/evaluate. I'll send it in the chat. I don't know, it's /. Oh yeah. I'm still replacing the lowest midterm with your final. If the final is higher. Yeah, that still stands. Yeah. Please, any other questions? Oh no, I think we have 3 more meetings and then that'll be it. Oh, including today. Yeah. So semester is closing really quickly. Okay, so if there are no questions, then let's get on to where we left off the last time. So is attendance going to be calculated into the grade? No, the attendance, you see, I awarded points for the midterms, right? So maybe I could award points based on attendance for the final, maybe, right? Yeah, but yeah, that's the statement on that one. Okay. Please, are there any other questions? Okay, feel free to let me know if any other questions come up as I teach, right? Okay, so now let me share my screen. I'm sharing my desktop now. If you can't see, do let me know. We are still on 5.2, right? Then the last thing that we did was to solve this problem, right? So last time we saw some properties of the integral, right? We started with this, right? You can flip the limits of integration and then you negate the integral, right? So if you are integrating from b to a of a function f of s dx, then you can just flip it and then you have to do minus of that, right? Okay, and then we said that when you integrate, you're integrating and then the limits of integration are the same, then that definite integral is equal to 0. And then we saw these 4 properties. Now, I explained how we obtain these 4 properties. As I said, you don't need the proofs, but the proofs is just to let you understand how we are getting these rules, right? So we went on to use the rules that we've learned to solve this. Now, I did this, but let me just walk through this. This was the last thing that we did. So because it's a sum, right, integral of a sum, you can just distribute the integral to each of the terms, right, like so, right? And then when you get here, for the integral of a constant, is always the constant times the length of the interval, right? So there is from 0 to 1, so it's just 4 times 1, which will give us what? 4 for the first piece. And then for the second piece, we can factor out the 3 because it's a constant. This 3 is a constant, it doesn't depend on the x. So you can factor the 3 out, and then you have 3, and then the definite integral, that's integral from 0 to 1 of s squared dx. And for that one, we had a result in 5.1, right? So later on, we will find ways of doing this, right? But for now, I'm just referencing this result from 5.1. So we saw this to be 1/3. So putting everything together, you get what? 4 plus 3 times 1/3, which is 5, right? So this was the last thing that we did. So now moving on, let's look at some other properties. There's also another important property, one of the most important properties you ever learned. So what this is saying is, whenever you're trying to integrate from a to b, right? And then you find some c, you're able to find some c in between the a and b, then the same as integrating from a to c, and then plus what? From c to b of the same integrand dx, right? Now, a very good way to understand this is using this graph, right? So suppose you want to find the integral from a to b, that's the area under the curve of f of x, right, from a to b. Then it's the same as finding the area under the curve for this piece, right, from A to C, and then finding the area under the curve from C to B, right? So if you look at it in this sense, then it becomes very, very obvious, like why this is true, you see. So that's it. That's the fifth property. Please, do you have any questions on the fifth property? Okay, then let's use the properties to try and solve this. So for example, 7, it is known that from 0 to 10, right, f of s ds is equal to 17. And then from 0 to 8, f of s is equal to 12. And we have to find from what 8 to 10. So right away, I see that, okay, the limits of integration for the first piece is from 0 to 10, right? For the second piece is from 0 to 8. And then this is what we are looking for. Okay, that's the third piece. But then I know that the integral from 0 to 10 of f of x dx will be equal to what? Integral from 0 to 8 plus integral from what? 8 to 10. So based on this, I can say, okay, since I'm solving these are known, right? That from 0 to 10, that one is 17. So I just plug that in there. From 0 to 8, that one is 0 to 8 is 12. And then plus what? Integral a to 10 f of x dx, right? And then from here, you can just do the integral from a to 10 of f of x dx. It's just going to be what? 17 minus 12, which is equal to 5. And then that's it. Please, I hope you get this. Any questions on this? Anybody needs time on this slide? Okay, now let's look at some more properties. Now, these comparison properties are useful when you are trying to find an integral, right? But you don't have a lot of information about the integral, but you can relate that integral to other integrals, right? Which have properties which are known, right? So for example, for number 6, what you're saying is before you even find an integral, if the integrand is what? Is positive, or let's say not positive, but non-negative, right? So this includes the non-negative part. If the f of x is a non-negative function, then for an integral from a to b of a function, ds is supposed to be greater than or equal to 0, right? So in the geometric sense, this adds up, because if the function is non-negative, then let's say it's either positive or 0, then it will be like the interpretation will be an area under a curve, and you can't have negative area. You see, you can't have negative area. Area can be 0, but it cannot be negative, right? So it makes sense. So whenever the function that you are integrating, the integrand is what? Is non-negative, then you can't get a negative integral, a negative definite integral, right? Okay. Now, another thing is if you have two integrands, and f of x and then g of x, and then f of x is greater than or equal to g of x for a given interval, then the integral of f of x over that interval should be greater than, or the definite integral of g of x integrated over that interval, right? Because the function f of x is bigger than the g of x, the area under the f of x, if they are both non-negative, that is, the area under f of x will always be bigger than the area under g of x if the f of x is bigger than g of x. Do you see the idea? Yeah. Now, the last part 8 says, if you have a function f sandwiched in between two constants, right, over a certain interval, then remember that when you integrate the m, the constant m, then it's just m times what? The length of the interval. The length of the interval is b minus a. So that's what's going to give us this lower bound. And then for the uppercase m, which is the upper bound, since it's also a constant, then the definite integral of that will also be what? M times the length, which is m times b minus a. So you, for sure, because this function is in between the constants, then the integral of the function is also going to be in between what? The integrals of the constants, which are m b minus a and then uppercase m b minus a. So that at least before you solve this, if this is something impossible to solve, at least you get an idea of what the range of values that it falls in. And this usually helps when you're trying to approximate like definite integrals. Okay. Please, anybody needs time here? Okay. So this is just explaining what I just talked about for the properties that we just saw here, 6, 7, and 8. And these are graphs showing the property 8. Right, so if you have the m here, and then the function is sandwiched in between this uppercase m, and lowercase m, then the area under this will for sure be in between them, right? Be in between the area between the m and then the x-axis, and then the area between the m and the x-axis. So the area between the lowercase m and the x-axis is just that this area. Then the area between this m and then the uppercase m and then the x-axis is this whole thing, right? Is this whole thing. So for sure, you see that the area for the f of s will be in between those two. Okay, and that's all for this section. Please, do you have any questions on 5.2? Finally, we are done. This is the longest session ever, 51 slides. Okay. Then let's move on to 5.2, 5.3. Okay, I'm sharing 5.3 PowerPoint now. If you can't see it, please do let me know. Now, this piece, for all the other stuff that we've done, a lot of them is like a lot of calculator work and approximations and stuff, right? And limit of sums and all those stuff. But 5.3 is where we get much more of like the simplified ways of finding integrals and all those stuff, right? So it begins here, right? Now, this is a fundamental theorem of calculus. Now, there is a relationship between differentiation and integration, right? So this theorem is going to establish that relationship, right? So this is saying that it establishes the connection between two branches of calculus. This is differential calculus and integral calculus, right? So you're going to learn two parts of this theorem. Now, the first part of the fundamental theorem, right? Fundamental theorem of calculus, which is the short form is FTC, right? So this FTC part 1. So the first part of fundamental theorem of calculus, right, concerns functions like this. So suppose you have a function g of x, and this function is in the form of a definite integral, in the sense that the lower bound is a constant a, the upper bound is a variable, right? The upper limit of integration is a variable x. So this g of x depends on this, right? The x here is the upper limit, right? The upper limit of integration. So if you have this function, such a function, right, then we are going to look at a theorem regarding how to get the derivative of such a function. So please note the structure. The constant is in the lower limit, and then the variable is in the upper limit, right? And then we have the integrand, right? So there's a kind of function. Well, you can see some of these functions appear in statistics. They occur in like highway designs and all those places. So it's possible you may see them depending on the field you are, right? So for this function, let's try and explain it, right? We know that, let's take the integrand to be a non-negative function. Then we know that like the function is, say, f of t can be graphed as a what? A function above the x-axis. Now, if you're looking at the integral from a to x of the function f of t dt, then that means depending on the x that you plug in, right, that will give you the upper limit, right? So say the x is somewhere in between the a and b, right here. Then this integral will become what? The area. This is the area under the f of t function, right? Area under the curve, this one. So we can vary this x, we can bring it here, and then that will give us this area. We can even bring it, you can push it forward here. We get an x here, right? And then that will also give us. So it can vary based on where we put our x. Do you see? So that's the structure of this function. So this is just explaining the function. Okay. So what does the fundamental theorem of calculus say about a function like this? So the fundamental theorem of calculus says, part 1, right? This part 1, there are two parts. This part says, if this integrand is continuous, right? Very important. If it's continuous on the interval, on the closed interval a to b, then a function g of s defined as this, where the variable s is dependent on, is in the upper limit of what? Integration. It's continuous, right? So if that g of s is continuous, if the f of t is continuous, then the g of s is also continuous. And the g of s will be differentiable such that the j prime of x is just what? The integrand evaluated at x. That's all. We are done, right? So if you want to find the derivative of a function like this, right, with this structure, then you're just doing what? The f, instead of using f of t, you're just doing f of x, and then that'll be the integral. That'll be the derivative. That's all. We are done. So another notation is you can just attach the differentiation operator to this integral, right? And then you are going to get what? The integrand evaluated at the what? At the upper limit x. So it's that simple. It's straightforward. Not too much thought into it. So I think it would be a good idea to see an example. Yeah. So this is just explaining what I talked about. So now let's look at this. This question says, find the derivative of this function. So we say, okay, j prime of x. That's the derivative. Okay, so what's the derivative? Well, the derivative of this, this function structure is like what the function structure we saw for FTC part 1. Okay, because it has a constant in the lower limit of integration, and then the variable x here is in the upper limit. Oh, nice. Now, immediately those two are satisfied. The question is this function continuous for the given interval? Yeah, this function is continuous for every t. So it's going to be continuous for this. So immediately I know that the conditions are satisfied. I say, oh, the derivative is just what? This integrand here. But this time I'll replace the t with the x. So it will just be 1 plus s squared. I'm done. That's all. Right? Yeah. See? So that's an application of the fundamental theorem of calculus part 1. And is that straightforward? Okay. Please, any questions here? Anybody needs time? Okay. So so this is just arguing that this formula may seem weird. You think, oh, who needs this? But as I was saying, they occur in several areas, right? In statistics, I mentioned statistics. It turns out they occur in physics, chemistry, and a lot of other areas. For instance, right, this is a specific example. The Fresnel function, right? The Fresnel function, which is given by this, is named after this, right? It's used in optics, right? So there are several ways where it occurs, right? And it's even been applied in design of highways. Okay, so that's FTC part 1. Please, any questions so far? We do more examples and see the dynamics. It can be more interesting than this, than just plugging in X. Okay, so now let's move on to part 2. So FTC part 2 says, if f is continuous, right, the integrand is continuous on the what? On the interval of for the limits of integration, intervals obtained from the limits of integration, right? Then we can just obtain that not by using limit of sums. So this is like a short rule that we can use to get the definite integral, not by doing limit of sums, but rather it is just going to be what? The antiderivative evaluated at the upper bound minus the antiderivative evaluated at the lower bound. You see? So that's why 4.9 is going to be very relevant under this section. So we are going to be finding, you'll be finding what definite integral just using antiderivative. As long as the integrand is continuous on that interval, then the definite integral is just the antiderivative evaluated at the upper limit minus the antiderivative evaluated at the lower limit. That's all. That's those two, right? And these will come to play a lot in this chapter. The entire chapter 5.3, 5.4 and 5.5 are all based on this second FTC, right? This second theorem. Okay. So please, do you have any questions here? Do you need time? Okay. Now, let's look at differentiation and integration as inverse processes. So from what we've seen, right, whenever you have, remember that antiderivative, how do we get them? For antiderivative, we're seeking functions which, say we were given a derivative and we're trying to find out the functions whose derivative is the function that we have, right? So differentiation and integration are inverse processes because we've related the definite integral as an antiderivative, like antiderivative evaluated at the limits of integration. So they are inverse processes, right? So this is just grouping everything together, what we've learned so far. So for the fundamental theorem of calculus, suppose the integrand is continuous on a closed interval a to b. Then for a function like this, its derivative is given by this. And then the integral, the definite integral, this is given by what? The antiderivative evaluated at the upper limit minus the antiderivative evaluated at the lower limit. So that's all. That's a summary of this whole thing. So the rest is just to do more examples. Please, any questions here? Okay. Okay. So this part is all about notation. For this slide, what we are talking about here is, because the derivative of the antiderivative gives us the integrand, we can just replace the integrand here. Remember, it was like this, a to b f of x dx. Because when we differentiate the antiderivative function, we get the derivative, right? So there's the integrand. So you can just put uppercase f prime of x here, and it's still the same thing. So if you see this, is the same, right? So that's all. So yeah, do you have any questions on the notation stuff? Okay, so a lot of you have come in by now. I made this announcement at the beginning. I'm going to give points for doing the course evaluation, right? The course evaluation. So when you are done, send me an email, right? Showing that you submitted the evaluation for the class, right? So yeah, that's just for you to know. Okay, so now this is just a list of examples. So let's just tackle these, right? So let's start with one. Let me make some room. So this one says differentiate the following. So for the first part, we are applying FTC part 1. FTC part 1, fundamental theorem of calculus part 1, right? Because it's about differentiating some integral function. For the second piece, we are going to find the definite integral by using FTC part 2. Fundamental theorem of calculus part 2. So let's start with the first part, A. Because there are a lot of them, please, I'll appreciate if you could help me with some of them. Right, so maybe start with this. For part A, what do you think is the answer? What is f prime? Right, so 1A, we are doing 1A. So let me start 1A. So when you give me the answer, then we all work it together. So what do you think? What is the derivative of this function for 1A? Anybody? Because I did an example earlier on, so feel free to free your mind on this. What do you think? 1A. What do you think the answer is? And it's not as long as it's satisfied that, just plug in the s in the integrand, that's all. Okay, I have negative sine t, that's good attempt, but try again. I think probably the notation questions. Perfect, Megan, that's correct, right? It's s cosine of x, right? So how are we getting that? So let's do it together. So 1A, let me do this. 1A, so we have f of x equal to integral 4 to x t cosine of t dt. Okay, so right here I say, okay, now I'm asked to find the derivative of something that involves an integral. Oh, so fundamental theorem of calculus part 1. Now the constant is down here, the variable is up there. Oh, nice, the conditions are satisfied. This function here, t cosine of t, is continuous everywhere. So it's going to be continuous on this interval. So for sure, I say, okay, I just need to plug the s in place of a t down here. So just s cosine of x. That's all. I'm done. See, x in place of t. So wherever I see t, I just put in x. That's all. Now let's move on to b. So for b, I have f of x equal to, that one is 5 to x. So cosine squared of t dt. So the thing is, for this one, I start, okay, is this function structure like what we saw under the fundamental theorem of calculus? Well, for this one, you can see that the constant rather is in the upper limit and the variable is down here. So the thing is, how do I switch? Is there a rule I can use to switch so that the variable will go on top? Can anyone help me with that? Is it possible? What can I do?
You switch the numbers and then negate.
Thank you. Perfect. Right? This is from the previous property. So what we can do is, I can just let the variable go on top. I'll just say negate and then flip. Perfect. Now, I have it in the form that I need it. Right? So now the derivative is going to be, when you're differentiating and you have a negative, by the constant multiple rule, just ignore the negative. And then I focus on all the derivatives. So this one, let me just attach the differentiation operator so that I don't do it directly, so that you see the transition. Okay, so then I focus on the derivative of this function. But the derivative of this function is what we just saw, right? This takes the structure for the FTC part 1 to be applied. So based on this, I'll say, okay, the constant is down, the variable is up here. Perfect. This function here is continuous for this interval. So the derivative of this second piece, the negative is written out. It's just cosine squared of x. And I'm done. That's all. Okay. Please, any questions on this example? B. Okay, then let's move on to C. For C, we have f of x equal to, that one is 1 to s cubed, and then sine of t dt. Okay, for this one, there is another different kind of, a different issue with this. The function is dependent on x, but I don't see x here. I see a function of x. The function depends on x, but this one is a function of x, right? But this one is more like, suppose you have, let me try and write this in this form. So say I can write this as, say, f g of x. If I set g of x equal to s cubed, and I set f of, say, x equal to what? Integral, oh, just went on there. Yeah, integral 1 to x sine of t. Please, you agree with this line? You understand I can do this, right? If I say the f of s is a composite function, I can see the f of s to be a composite function. Why? If I partition it, if I break it down to a composite function, I can select my outer function to be this f of x, which is now integral from 1 to x sine of t dt. And then if g of t is s cubed, then for sure f of g of x will be plug the g of x in place of x, right? For the f of x, right? So that will be just 1 to s cubed sine of t dt. You see, so I get back the original. So for a function, whenever it's not directly the x, then you can look at it as a composite function. And if you're looking at it as a composite function, then for its derivative, which rule will we be using? Do you remember? This is a composite function. So what rule? Do you remember? I mean, it's been a while, but what rule? The derivative of composite function. What's the rule we are going to use? Perfect. The chain rule. The chain rule. So by the chain rule, all that we have to do is just identify your inner function. Identify your outer function. And then apply, right? Differentiate the outer function, plug in the inner function, times the derivative of the inner function. So for this setup, right, the inner function is just going to be this function. So this s cubed is our inner function. Right? So in this case, the g of x, you see, is our inner. Right? G of x is this. And then the f of x is our outer. Okay, so now let's do this. So let's differentiate the outer function. So the thing is, differentiating the outer function, what does that entail? The outer function is this structure. It has the constant down here and a variable here. So if we're differentiating, we would have plugged in the x. But don't forget that when we differentiate the outer function, we don't plug in x, we plug in the inner function. So that means for the first piece, when we differentiate the outer function, it will just be sine of what? Plug in the inner function. Right? When we differentiate the integral, we plug in the variable. But because the inner function is s cubed, just plug in s cubed. So we have sine of what? S cubed. Times the derivative of the what? The inner function. Right? So just plug the inner function in there times its derivative. And then that will give us what? This 3s squared and then sine s cubed. That's how we do it. Please, are you okay on this? Does it make sense? Do you have any questions? Is there any part you want me to explain again? Is there any part you want me to explain? So the key is, well, you can think of it as, if it's x, I'll do the same thing. In simple terms, always just plug there, as long as the variable function is up there, just plug it in, times the derivative of that function. So if it's x, I don't lose anything by using that concept, because if I plug in x, I get what? S cosine of x, times the derivative of x is 1. I still get s cosine of x. Do you see? For this second example, I'll put it in my mind. Okay, as long as the variable term is up there, just plug it in and then multiply by its derivative. So if after turning it using the negative sign here and switching the limits of integration, I was okay, plug the s in, I guess cosine squared of x, right? Times the derivative of x. The derivative of x is 1. I don't lose anything, I get the same thing. For this one, I'll say, okay, the variable term is up here, the constant is down. Okay, so plug it in, sine of s cubed times the derivative of s cubed is 3s squared, and done. I just jumped to this point. All that I went through was to explain so that it makes sense. But when you are trying to use this on an exam, in an exam setting, it's best you think about it in that term, right? In those terms. So just plug the function in times its derivative, right? Another trick you could have employed is, what is the derivative of a constant? The derivative of a constant is 0. The derivative of a constant is 0. So for this one, I don't even need to flip. I can say one trick I can apply is, okay, plug the 5 in, right? Plug the upper limit in. If I plug the 5 in, what is it? Or let me start from A. For the first piece, I'll plug x in, cosine of x, right? Multiply by its derivative, that will be 1. I'm done. And then minus, right? Plug the 4 in. You get 4 cosine of 4 times the derivative of 4. What's the derivative of 4? 0. That goes off, right? So there are several tricks you can employ so that it simplifies matters. Yeah, that's what I'm just trying to put across. But do you have any questions so far? Okay. Now let's look at a very interesting scenario. Here, I chose the examples carefully so that it covers all the possible cases you get on your homework, right? So let's look at D. D is an interesting one. So for D, we have f of x equal to s squared. No, go back. Yeah. So s squared, 2s something, 2s minus 1, 2s minus 1. And then e to the t squared dt. Okay, so this is what we have, right? So let me first explain so that this makes sense, and then we use the simplified way to solve this, right? So in doing this, we realize, oh, the denominator is dependent on x. The numerator, not what did I say denominator? The lower limit of integration is dependent on x, and then the upper limit of the integration is also dependent on x. So say, okay, the structure is not like what we know the FTC part 1 functions to follow. It's not like that. But what can we do here? Well, we can introduce a constant ourselves, right? Remember that if we find a constant in between the s squared and 2s minus 1, I suppose we have a constant here. Then from the rules that we learned, if there is a number in between the intervals, then we can integrate from the lower bound to the number there, and then continue from the number to the upper bound. Do you see? So if we identify a constant a, which is in between the functions, then we can break this f of s piece into this. It makes sense to say this is what? First, we do from what? 2s squared, lower bound to a constant, and then e to the t squared dt, plus integrate from what? A to what? To the upper limit of integration, and then what? E to the t squared dt. Please, I hope this makes sense. Right, this is rule 5, the rule that we just learned in 5.2. Here, a is a constant. Let me say constant. Okay, so if we have that, then for the first part, right, which is this integral, because the variable term is down here, is in the lower limit of integration, I'll need to bring it up. So for that one, I'll just negate and flip. And then for the last piece, that one, the constant is in the lower limits of the integration. So that one, I'll just leave it like that. So this is where I am now, right? So now, what is the derivative going to be? I think I'm going to move this here. So for the first piece, just leave the negative out. And then when you're differentiating this, what do? Just plug this variable, the variable term, the function here, which is the dependent on the x, in there, in place of t, and then multiply by the derivative of that function. So that just be what? E to the what? T squared is now going to be 2s minus 1 squared times the derivative of the 2s minus 1, which is 2, plus And then for this one, you plug in s squared. So that'll be your e to the what? S squared in place of t, and then squared times the derivative of s squared. The derivative of s squared. So that means you are getting what? F of s equal to what? So minus 2 e to the what? 2s minus 1 all squared, right? And then plus the derivative of s squared is 2x, so 2x e to the what? And then e to the s squared all squared. That's just going to be e to the 4. And that'll be your final answer, right? You don't have to go through all this. You can just use the simple rules that we learned, right? So it's always going to be plug in. So for this one, I'll just say, okay, plug in the upper limit. If I plug the upper limit in, I get this 10 times its derivative. The derivative of s squared is what? 2x. So that'll give me this. And then minus, plug in the lower limit, right? So minus, plug in the lower limit. If I plug this in there, I get a e to the 2s minus 1 all squared times the derivative of the lower limit. So that'll be the derivative of 2s is what? And minus 1 is 2, right? And then you have it straightforward. So you can just jump from here to here by using that shortcut. Always plug in the lower limit times the derivative of that lower limit. Minus, plug in the, what did I say? Plug in the upper limit, sorry, right? Sorry, let me make this straight. Always plug in the upper limit. If it's asking for the derivative, plug in the upper limit. Multiply by the derivative of the upper limit. Minus, plug in the lower limit. Multiply by the derivative of the lower limit. And then that's all, right? That's how it's always going to be. So you can, that's a more general way of seeing this. And with that rule, you can solve all of them easily. Plug in the upper limit times its derivative minus what? Plug in the lower limit times its derivative. You can use that on this, on all of them, it will work. You don't have to go through all the algebra. So for the first one, plug in the upper limit. That'll be s cosine of x minus plug in the lower limit. So plug in the upper limit, s cosine of x times its derivative. That'll be 1. So that's s cosine of x. Minus plug in the lower limit, 4 cosine of 4 times its derivative. That'll be 0. So the second part will go away, and that'll give you this. This second piece, you don't need to go through all this flipping. Plug in the upper limit, cosine squared of 5 times its derivative. That's 0. Minus plug in the lower limit, negative cosine squared of x times its derivative, 1. You get this, done. For this c, plug in the upper limit, sine s cubed times its derivative, 3s squared. So 3s squared sine s cubed. Minus plug in the lower limit, sine of 1 times its derivative. The derivative of 1 is 0. That goes to 0, and you get this. So you can just jump from here to here. So you can just look at them and get your answer without having to go through all the algebra. But I need to do the algebra so that you understand and then it makes sense. But please, any questions on these kinds of problems? On the getting the derivative involving an integral? Okay, so then that's it for FTC part 1. Now let's look at FTC part 2. Right, for these ones, we'll be evaluating these definite integrals with what? Using the antiderivatives. Now, my question is, suppose I ask you to find the derivative of this function. What will be the answer? 2a. What's the derivative of 2a? Anybody? What's the derivative of the first definite integral? Anybody? What do you think? What will be the derivative of this? Assuming I set f of s to be equal to this, and I say find a derivative, what will be the derivative? Close, close, Nicholas, you're close. You're giving me something, but you're close. Okay, so let me take it from this angle. If the function, say here, s cubed, I know s cubed has some parts which is non-negative, but for this interval 1 to 3, s cubed is a positive function. What is a definite integral? How can we interpret it? It's going to be what? Net area or area under a curve, right? So what is the derivative of an area? An area is constant. The derivative is 0, right? Because this one does not, the limits of integration is not a variable. You are going to get a constant. The derivative of a constant is 0. That's why they don't even bother you. They don't bother to ask you to get the derivative of this because it's just 0. right? Okay, so that aside, let's try and solve these. Right, so let's look at A. So 2A. For 2A, we are asked to find this definite integral. This one, no variables. And it's not asking us to differentiate. It's asking us to what? Evaluate this or get this definite integral. Right, so 1 to 3, s cubed dx. So what we just learned in FTC part 2 is whenever you're given a definite integral, and then you're asked to evaluate it or find the definite integral, the first thing you have to check is the integrand continuous on that interval. In this case, s cubed is continuous everywhere. So it's for sure continuous on this interval. Nice. Immediately that is satisfied, then you can obtain this definite integral by finding the antiderivative of s cubed and then evaluating it at the upper limit minus evaluating it at the lower limit. So the question is, what's the antiderivative of s cubed? The antiderivative of s cubed is what? That one, we use the power rule version, right? For antiderivative, it's just 3 plus 1 over 3 plus 1 plus c, right? Now, immediately you take the antiderivative. You don't do the integral sign again. You do something like this, which which implies that you are going to evaluate it. Some like to do it like this. Some like to use this. 1 to 3, either this or this. Either one is right. So for this one, let me simplify. Either this or this. You can either use this or this. It just means that you are now going to plug in, right? You plug in the upper minus what? Plug in the lower, right? So immediately you do this, just plug in the upper, right? So when you plug 3 in, you're going to get 3 to the power 4 over 4 plus c minus what? 1 to the power 4 over 4 plus c. Now, because the c, which is the arbitrary constant, is still a constant, when you plug, no matter the number you plug in, the c's will be the same for the two sides, right? And because you'll be subtracting, the c's will always cancel out. So when we are working definite integrals, we don't even worry about the c, right? We don't worry about the c. But I brought it the first one because this is the first example. But for next ones, because the definite integral and the c's will be the same, they'll cancel out, right? You're doing minus, they will always be c. It will always be the same c, and it will cancel out always, as long as it's a definite integral. I won't even bother bringing the c, right? So then everything reduces to 3 to the power 4 minus what? 1 to the power 4 over 4. So 3 to the power 4, that's just going to be 81. So you have 81 over 4 minus 1 to the power 4 is 1, and then over 4. So that's just going to be what? 80 over 4, right? Which is 20. And that is my definite integral. I don't even have to do any limit of sums. But if you do limit of sums, you get the same answer, right? But these, as I said, they are like the rules under integration. We don't do it from first principles. Just use the rules and then you have it. Okay, so then let's do more. That was the first one. Let's do more. Let's do the b. b is 0 to pi 2b is 0 to pi on 2 and cosine of something. Cosine of x, okay, dx. Okay, so now for this question, it's a definite integral. We are trying to find this definite integral. The question is cosine continuous on this interval? Yeah, cosine is continuous everywhere. Nice. Immediately we realize that there is, okay, let's find the antiderivative. What's the antiderivative of cosine? Anybody? Do you remember what's the antiderivative of cosine? Do you remember?
Sin x.
Perfect. Thank you. It's sin x. So you just write the sin x. I need to do plus c, but as I told you, with definite integrals, the c won't be relevant. So I just do this, then do 0 to pi on 2, right? And I plug in pi on 2, that'll be sine of pi on 2. And then minus or plug in 0, that'll be sine of 0. So what is this? Sine of pi on 2, what is that? Sine of pi on 2 will be what? Square root of 3 over 2. Right? Yeah. No. What did I say? No. This one is square root of 2 over 2. Okay, so that will be sine of pi. I can't erase here. Let me go back. Okay. Draw, erase. This is like sine of 90 is 1. Shift 5. That'll be 1. 1 minus sine of 0 is 0. So you get 1. That's all. Okay. I hope you get this so far. Any questions so far? Okay. Anybody needs time on this? So please revise your antiderivative. They are going to be very relevant going forward. And you do a lot of this in Calc 2, right? Calc 2 will be around that. Okay, so let's do C, -1 to 0, e to the x. C, -1 to 0, e to the x dx. Okay, e to the s is continuous everywhere, so it's continuous. Okay, nice. Next, get the antiderivative. What's the antiderivative of e to the s? That one is easy. It's just e to the x. And then evaluate from -1 to 0. So plug in 0, get e to the 0 minus what? E to the -1. So that just be what? 1 minus e to the negative. I'm done. I don't even have to do any limit of sums. You see, that's the power of this theorem. It's very, very powerful in that respect. You don't have to do limit of sums for these definite integrals. Okay, please, any questions on this so far? Are you okay? Okay, so if you're okay, please help me with D. Oh, D is, oh, I should have given the easy one. Okay, please see if you can, almost time. Okay, let's do it together. Let's do D together, right, D. Okay, D, we have 1 to 2, and then 3t plus t to the half over t squared dt. Okay, this is going to take some time. That's why I wanted to give you this last one, but let's do it together so that we exhaust everything. Then we have time for this. Okay, so let's do this. Now, for this, I say, okay, do I have a direct antiderivative for this? Is the function even continuous? Is the integrand continuous on this interval? The integrand will be discontinuous at 0, and this interval doesn't cover 0. So we are good, right? The only number which will make this undefined is not in the interval for the limit of integration. So we are good. So all that we have to say is, okay, do you have a direct antiderivative for this? No, we don't. But can we do something to get the antiderivative? Yeah, we can, right? So let's just take, so I just write 1 to 2 here. I'll say, okay, for the t squared, I can distribute it here since it's a monomial. I can do this, right? Okay, I can simplify further, right? So this gives me 3 over t, right? The t's will cancel. I get 3 over t, and then plus what? For this one, I can do t to the what? Half minus 2. I'm still bringing the integral sign because I've not yet taken the antiderivative for this one. So I still have to bring the integral to remind me of that, right? I can't plug in yet. So now when I get here, I say, okay, this one is 3 over t plus half minus this is going to be t to the negative 3 over 2. Then the t, integral 1 to 2. Now that I'm here, for this structure, I can get the antiderivatives for each term, right? Don't forget that when you're doing a definite integral term by term, like for 2 terms, you can do it term by term. So let's get the antiderivative for the first piece, 3 over t. For the first piece, 3 over t, does anyone remember the antiderivative for this function? 3 over t. Perfect, thank you. It's just 3 ln of what? Absolute value of t, perfect. And then for the second piece, this one is, we are going to use the power rule, right? So it's just going to be t 3 over 2 plus 1 over negative 3 over 2 plus 1. And then you evaluate it at the what? At the limits of integration. Right. I'll need to move on to the next slide to continue this. Do let me know if you need more time here. Okay. So that gives us what? Let's simplify. You have 3 ln of t. Oh no, absolute value. Absolute value of t. And then for this piece, negative 3 over 2 plus 1, that's just going to be negative 1 over 2. So that piece will give me minus 2, right? And then I have t to the what? And negative 3 over 2 plus 1, that's just going to be negative 1 over 2, like this. Yeah. And then I'm evaluating from 1 to 2. So then I plug in 2. That'll be 3 ln of, absolute value of 2 is still 2. So I can just do ln of 2 minus 2 times 2 to the negative half and then minus. The next time I plug in 1. So that'll be 3 ln of 1 minus 2. Let me bring this down. Minus 3 ln of 1 minus 2, 1 to the negative half. Right, so everything reduces to this side is, yeah, you can just put in this answer to accept it, or you can simplify further. You have 3 ln of 2, this minus 2 over square root of 2, and then minus 3, ln of 1 is 0, so that'll go off. So you have minus 2 again, and that'll be your answer. Yeah, and it's time. Yeah, so that's all on today. Thank you for your time, and if you have any questions, please feel free to reach out. Right, so all the best. Enjoy the rest of your day. See you on Friday. You're welcome. You are welcome.
See you, Matthew. Have a good day.
And to you, Danny.